Hello, my name is Amirali Babavalian. I'm a Ph.D. student at Texas A&M University. I'm working under supervision of Dr. Zallinger. In this presentation is regarding investigation of deicing salt solution in the process of calcium oxychloride formation in cement paste. The whole project is comprised of an investigation into the role and extent that joint sealant effectiveness plays on the durability of seal transverse socket joints in jointed concrete pavements that are subjected to freeze-thaw condition and de-icing salt solutions. In the right picture, you can see some damages on concrete pavements because of the freeze-thaw. And as I've mentioned, there are some deteriorations in concrete pavement joints because of the application of de-icing salt solution. And this kind of deterioration is more common in Midwestern parts of the US. In the picture, in the left one, you can see that how is the saw cut joints. You can see different parts of that. You can see the initial cut and second cut and the joint sealant as well. In the right one, you can see that the debonded sealant or joint sealant failed leads to penetration of water salt solution into the joints. Which leads to the deterioration. In this picture, you can see different physical evidence of joint deterioration and progression of distress from core samples from the fields on concrete pavements. As I've mentioned, this deterioration is because of the formation of calcium oxychloride or KOC, as a result of chemical reaction between calcium hydroxide and chlorine. Chlorine is coming from chloride-based de-icing salts such as sodium chloride, magnesium chloride, and calcium chloride. In this research, we tried to see the simultaneous effects of different parameters, including water to cementitious ratios and materials, and the salt solution concentration, and especially temperatures. And the main goal of the whole project is getting the activation energy of this reaction. And that, as you know, the activation energy is the energy which is needed to initiate the reaction. In this picture, you can see an example of how to get the activation energy. And you can see that slope of the plot of the inverse of time to failure data versus the inverse of the temperature data times the universal gas constant gives us the activation energy. In this regard, we did the TGA test, thermogravimetric analysis test, and also visual observation, which in the following, we can see that temperature is a key parameter affecting the formation of KOC. The samples that we made were cement paste cubes by the size of the 2 by 2 by 2 inches, and we used Portland cement type 1-2, distilled water, and the water to cement ratios of 0.38, 0.43, and 0.48. The salt solution concentration that we exposed our samples to them was 10%, 20%, and 30%, and we used reagent grade calcium chloride dihydrate. We didn't use the sodium chloride because based on the last studies, they saw that the sodium chloride will not lead to KOC formation as much as calcium chloride and magnesium chloride. After preparing the sample for the curing process, we put the samples in the 100% humidity room and the temperature of 23 degrees. And after that, we put the samples in 3 different rooms with different temperatures of 4, 20, and 40 degrees Celsius. For the TGA test, we tested the samples after putting in these different rooms and exposure to different salt solution after 7 days, and visual observation was conducted after 28 days. Here in this slide, you can see the device that we used, which is a gravimetric analyzer. The right picture shows the grounded cement paste pass sieve number 200. And in the left side, you can see the alumina pan, which was used for this test. We used the alumina because we heated our samples until around 900 degrees. So we couldn't use the aluminum pans. The reason that we use the TGA test is that here you can see the chemical reaction that leads to KX formation. In the left side, KX hydroxide and chlorine reacted together to form calcium oxychloride or KX. The heating rate of this test was 10 degrees Celsius per minute, and the decomposition of calcium hydroxide occurs approximately between 350 and 550 degrees Celsius. So based on the results that we get from the TGA test that you can see in this picture, the decomposition of calcium hydroxide is occurring in this area. So we can get the amount of the mass loss of the samples in this part. And the greater mass loss shows we have more calcium hydroxide in the sample. And more calcium hydroxide tells us that less amount of calcium hydroxide participated in the chemical reaction. So it leads to having less amount of calcium oxychloride. And as I've mentioned, the visual observation was conducted on after 28 days of exposure to salt solution. Here in this graph, you can see the amount of the mass loss of the specimens obtained from conducted TGA tests on different samples exposed to different salt solutions with same water to cement ratio of 0.38. And in the top of that shows the samples that was not exposed to the to the salt solution concentration. So as you can see, we have more amount of calcium hydroxide because none of the calcium hydroxide participated in that reaction. In this picture, you can see that the samples exposed to 10%, 20%, and 30% of salt solutions with water to cement ratio of 38 and in the temperature of 20. As you can see, these two samples for 10% and 20% have approximately same crystals of calcium oxychloride. So if you compare it with this graph, we can see that for 20 degree, the 10% and 20% have same amount of values. So the pictures verify the values obtained from the TGA test. And in the 30%, we can see less amount of calcium oxychloride. That you can see here, we have more calcium hydroxide, so we have less calcium oxychloride. In this graph also, you can see this results from samples with different water to cementitious ratios and the temperature of 4 degrees Celsius. In this picture, you can see the areas with more concentration of presence of KXC crystals. And this table is a summary of the result we obtained from TGA test that I will explain it a little bit in the conclusion part. By increasing the water to cement ratios, it's obvious that we have more calcium hydroxide. So we have more potential for KXC formation, but this the other parameters may lead to forming a less KXC. Changing the values of water to cement ratios influences the effect of temperature on the formation of KXC. Unlike for a lower water to cement ratio, by increasing the reaction temperature, we saw that the KXC formation decreased. And also by increasing the water to cement ratio, we know that we have more KXC formation, which was shown more. Actually, this formation, this KXC formed especially for those samples that exposed to lesser salt concentration. In other words, we can conclude that to compensate the effect of increasing the water to cement ratios, an increase in salt solution concentration may result in lower KXC crystal formation, so we may have a lower rate of deterioration in concrete. And as you saw in this picture, it can say to us that when we have more cracks in our samples, it leads to formation of more KXC crystals. So we can suggest that minimizing the amount of cracks that we have in our concrete pavements may lead to limit the KXC formation. Thank you for your attention. Can you still hear me?